Hi everyone. So today I will be going over some practice problems for my Organic Chemistry 2 exam. Alright, so this is a series of review problems. So I won't be showing every single step for some of these because I'm assuming that you have some kind of basis in this, or some of this will look slightly familiar, hopefully. If not, hopefully this teaches you something. Hopefully you learn from this if you're completely lost in your class like I am sometimes. But yeah, so without further ado, let's just start. I'll be putting timestamps to these problems in the description. So if you want to jump ahead to a specific topic, go ahead. And feel free to pause at any time if you want to try to solve the problem yourself on the screen. Very helpful. So for question number 1, there are actually 2 parts to this, so we're just going to be doing them one at a time. We want to give the carbonyl and amine that can be used to form a compound. And we're going to be given the compound. So for 1A, we're given this compound. All right. So pause here if you want to try to solve this. If not, I'm just going to go ahead. Now, we don't need to draw the whole arrow pushing reaction mechanism for this. We just want to know what carbonyl and what amine we need to use. And to do this, we can use a very, very nifty trick. We'll just draw a line through this carbon-nitrogen double bond. And from there, let's draw what is on each side of that line. Okay, now let's start over here with the side that includes our nitrogen. That's a big hint because remember that amines contain nitrogens. So we know that over here, we already know that this is our amine. We just have to draw the correct amine. Now, remember, we've disconnected this bond, and so this nitrogen is no longer double bonded to this carbon. So what's going to happen to this nitrogen? Well, remember that nitrogen is trivalent. It forms 3 bonds. It can form up to 3 bonds. It can form up to 3 bonds and hold a neutral charge. If you're thinking of ammonium, yes, but that has a positive charge. That's a tangent. So we can actually remedy this by forming 2 bonds with hydrogens here. Not hydrogen bonds, 2 bonds with hydrogen. And so this is our amine. Pretty simple. Over here, we know that there has to be the carbonyl because we have the amine on the other side. And to do this, we already have a C with 4 electrons. We just need to add an oxygen here. And if we want to be really specific, can you guess what kind of carbonyl this is? There are 2 kinds. And this is a ketone. And we can tell because if we look at this carbon, which is attached to the oxygen, it is bonded to 2 other carbons. So we know that this is a ketone. So using this disconnect method, we can solve this problem, these kinds of problems, very, very quickly. And for the record, this compound is called an imine. So if you take a carbonyl and an amine, you form an imine. So using that method, let's try to do this problem. Oh, that's not a triple bond. All right, try to do this one. Well, once again, we're going to disconnect it here. We're going to draw what's on each side. Okay. Now, let's start with the side with the nitrogen. we're just going to give it two hydrogens. And we have our amine. Nice and simple. This side might be a little bit more tricky because we have a carbon chain and it's written in this format where you can't just plop the oxygen wherever. Well, remember that carbon can form up to 4 bonds, and so we can add the oxygen. Actually, if we draw out the skeleton for this, it's a 2-carbon chain, so we can start with this. One of these only has 1 hydrogen added to it so far. And so we'll just add the oxygen up here. I forgot to draw this double bond here that it would have otherwise been connected to. But actually, the easier way to draw this would have been like this. This is the more accurate way to draw this. This is a skeleton, the structural formula for it. And this is our carbonyl, but to be very specific, this is our aldehyde. And the way we can tell is that this central carbon is bonded to a hydrogen. It's not bonded to 2 carbons, it's bonded to 1 carbon and 1 hydrogen. So it's an aldehyde, not a ketone. Okay, question number 2 involves a conjugated system that looks like this. A diene, if you will. Prefix di meaning 2, ene meaning carbon-carbon double bond. How will it react with this compound? So you might be tempted at first to try the Diels Alder mechanism. That's a very good guess. However, we want to look at the requirements for the Diels Alder. And so the relevant one here is that Diels Alder likes the cis conformation. It likes the cis conformation. So like this, where your 2 alkenes are facing the same side. It does not favor the trans conformer, in which the 2 alkenes are facing opposite directions. And the reason for that is because it's going to be very hard to get the overlap between orbitals necessary when the diene comes to attack. It's going to be very hard to get these orbitals to overlap all at the same time. So if we have a trans conformer like this is trans, we're not really going to see any reaction. So here, there's no reaction. Now you might be saying, if you're really, really clever with organic chemistry, which I'm not, but let's say you are, you might say, well, wait a minute. Can't these convert back and forth into one another? Well, yes, they can. These bonds can rotate. However, notice that over here, these are chains of carbons. They're just long chains of carbons, or short chains in this case. Here, we have the carbons in rings. So each carbon is already bonded to another carbon. And so it's going to be very, very hard, if it's going to happen at all, for this to interconvert back into the cis. You can try to draw this in the cis conformation, but it would require the double bonds to literally jump around if you were to move it. There's no easy way to move around these double bonds so that you can get the cis conformation. Maybe no, you're not going to be able to get anything. So because it's, if you want to use the proper term, it's locked in the trans conformer, there will be no Diels Alder reaction. No Diels Alder. That's a bit of a tricky one. For number 3, we want to show the steps to the Fischer esterification. And in this case, we're starting off with a carboxylic acid. Carboxylic acid. Now, for the sake of simplicity, I'm going to just use R groups to represent our alcohol. So if you remember, Fischer esterification uses, in addition to your carboxylic acid, it needs 2 things. It needs an alcohol, ROH, and it needs H+. So this will happen in acid conditions, and we're going to see why. So there are two big reasons why we need that H+. If we just add the carboxylic acid and our alcohol, you're not going to get the Fischer esterification. You need this H+. And yes, I know that technically this is an acid, it gives off H+, but that's not good enough. We need something a bit stronger. So in this case, in this problem, we're being asked to draw the arrow pushing. So let's do that. This one is pretty textbook standard reaction mechanism. So if you want to skip this, go ahead. Otherwise, I'm going to show you exactly how this works. So our first step is actually, this is old. So our first step is actually going to involve the H+. What we're going to do here is have these lone pairs, one of these lone pairs on the oxygen grab this positively charged hydronium. Remember that this is, or H+. Remember that this is negatively charged. Oxygen is very electronegative. It's going to pull in a hydrogen ion. And so we're going to actually get this intermediate now. But we have to be careful because now that we have some positive charge from this hydrogen here, we used some of those electrons to pull it in. This OH group at the end has lost, or rather it has gained positive charge because it has used electrons to bond with the hydrogen ion. Now notice here that the hydrogen ion was used to, or actually we'll see this in the next step. Next we have our alcohol here, ROH, and this oxygen on the alcohol is also very electronegative. And so it's going to attack over here. And the reason for that is because of this H+, making this a more unreactive species. It's doing something called activating the carbonyl. So that's the first reason why we need the H+. If we don't introduce the H+, this step over here is not really going to happen in any meaningful way. But this is going to happen if we introduce the charge here. If we make this carboxylic acid, if we create this intermediate where the hydrogen is bonded to this oxygen up here. Yeah, a lot of carbons, carboxyls, carbonyls, a lot of words that sound very similar to each other in this subject. And so what we're going to get is ROH bonded to this tetrahedral carbonyl. Now this is tetrahedral. Before it was not. Before it was not in the tetrahedral geometry. Now it is. It's bonded to 4 different things. Now the next step is actually going to involve another alcohol. It's going to perform a proton transfer, and in this case it's actually going to take from the alcohol that was bonded. And so now, oh, I forgot to show a very crucial step. I apologize. This would actually break the octet rule if you showed the arrows like I do. So we have to bring one of these electron pairs up back into the oxygen here. And that's going to cancel out this positive charge. It's also going to remove this double bond. So sorry if anyone caught that and realized that I was making a mistake there. All right, and so from here, this is decently straightforward. Well, remember that I said that we have 2 uses for the H+. We haven't used the second one yet, and it's going to come into play here, and it's because this OH group has lone pairs again, and the oxygen is going to want to grab the H+. And what that'll actually do is it'll make this H2O, or OH2 plus here. It's the same thing, H2O, OH2. And this is a very good leaving group. This is a good leaving group. So we're actually going to bring a lone pair of electrons down back here. So it's going to turn back up where it was before. And we're going to get this intermediate. So the second use for the H+, second use was to make OH into OH2 positive. And the reason that's key is because that makes it a good leaving group. OH is not a good leaving group. If OH were a good leaving group, you would have your bottles of beer and vodka reacting constantly because that OH bonded to the R would be so unstable. No. You need to make it into OH2, and you're going to use that with H+. You're going to do that using H+. And our final step is we're going to get another proton transfer from ROH. It's actually going to remove this hydrogen. So finally we can free up that pair of electrons that's been there since the first step. And we're going to end up with our ester. So as you can see, through a series of proton transfers and nucleophilic attacks, we went from carboxylic acid to ester using the Fischer esterification, and we used H+ and an alcohol. Okay, that was probably the most tedious problem here because it wasn't solving something, it was just, do you know the steps? Do you know the steps? Okay, so the next problem that we have is a synthesis problem. So we want to synthesize this ester. Okay, that's pretty simple, but there's a catch. There's a catch. We can't just use any method to do it. We have to use a halide. We have to use a halide to do it. So we can't use the Fischer esterification. We have to use a halide. Oh, wait, is this the wrong problem? Oh, I'm looking at a different problem. Sorry, folks. It's the wrong problem. Oops. Yeah. Do I want to edit that out? I'm not going to edit that out. I'm not going to do that. Okay. Alright, so we are starting off with this aldehyde for number 4, and this one is a reaction, so we're going to get a set of reagents. We're going to get 3 sets. The first one is CH3, CH2, MgBr. Second is H3O+, and the third is Na2Cr2O7, H2SO4. So I'm not going to draw the arrow pushing for this. I might draw it for the first step, just because it's very useful to know the first step's arrow pushing. But yeah, so the way we want to do this is, obviously we want to do this step by step. If you're really good, you can look at this and say, oh, I know what this is going to do. But for the rest of us, we have to take this step by step. So let's start with step 1. Well, if we notice, we see MgBr. That should set off an alarm in our brain that this is going to be a Grignard reaction. This is a Grignard reaction. Because that's a Grignard reagent. The C, the carbon chain, and the MgBr. That's a Grignard. So let's remember how Grignard works. We're going to try to draw out the compound, MgBr. And we want to remember that in Grignards, this is a very, very rare case of a nucleophilic carbon. This carbon over here is going to be nucleophilic. And so it's actually going to attack our carbonyl at this carbon and push that one of those pairs of electrons back into the oxygen. And so it's going to form an alkoxide. But remember that this carbon chain will attach. So we're actually going to get this. So this carbon chain, 2-carbon chain, attaches to the central carbon, and we get an alkoxide intermediate. Now, remember, so that's step 1. That's step 1. For step 2, we have H3O plus, which is the same as H plus, and virtually the same in chemistry. They mean the same exact thing. All right, this reaction is this is very straightforward. We have a negative charge here on the alkoxide. It's going to attack the positive charge on the H plus, and we're going to get an alcohol. So steps 1 and 2 combined are the Grignard reaction. You can have just step 1 and it's still a Grignard reaction. You only really need the first step to do it. But if you add step 2, that's how you get something useful like an alcohol. Otherwise, it will stop at the alkoxide. And finally, the third, I'm not going to draw the arrow pushing for this because I don't want to. That's complicated. This is an oxidizing agent. Oxidizing. And if we oxidize alcohols, this is step 3. If we oxidize alcohols, what do we get? We get carbonyls. So it's going to turn this OH into a carbonyl. And so this is our final product. And if we want to name it, let's say that they ask you to name it, it's butane-2-one. This is a 4-carbon chain. Good way to remember it is monkeys eat purple bananas. So methyl, ethyl, propyl, butyl, 1, 2, 3, 4. This is a 4-carbon chain, so it's butyl. And the carbonyl is on, the ketone, to be more specific, is on carbon number 1, 2, 2. So butane-2-one. Now you might say, well, why doesn't this... Okay, so you might say, well, I remember this being a very strong oxidizing agent, and you're correct. So why doesn't it form a carboxylic acid? Well, that will only happen if this is a primary carbon. So if we had the OH at the end, then yes, we would form a carboxylic acid. But this is on a secondary carbon. And so it will only form up to the ketone. It'll stop here. No matter what reagent you use, it cannot add, it won't be able to form another bond. Like it'll break the octet rule. Okay, so that's that reaction. Step 5, reaction. Yeah, number 5 is also one that I'm not going to draw the arrow pushing for because it's we don't have time for that. We have a lot of problems to go through. But we're starting off with this alkene, and we're going to react it with ozone and CH32S. Okay, now you might remember this from Orgo 1. And you'd be correct, this is an Orgo 1 reaction. This is just going to be ozonolysis. That's a weird way to write Z. Ozonolysis. And the way we want to do that is we're just going to split this bond and add oxygens to each end. And we're done. And if we want to name this, you want to practice naming them, you can pause the video and practice naming them. This will be propanone. Remember, one means ketone, so 1, 2, 3. This is propanone. And over here, this is ethanol. Remember, suffix al means an aldehyde. This is a 2-carbon chain, 1, 2. This is, so it's ethanol. Now, on your test, or on your homeworks, or in real life, you might see this written as DMS. It's the same thing. DMS means dimethyl sulfide. Here we have two methyls and a sulfur. So it's the same thing. We are on question 5. Okay. Question number 6. In this case, we're given a starting compound. So I'm going to draw that now. And we want to get a target compound. So I guess, this is kind of what we learn chemistry for. We have an A and a B, and we want to know how to get there. So if you want to try this yourself, pause it. I'll give you a hint. There are 3 big steps that we have to do for this. Okay, so the first thing that we notice is that, well, we're literally getting rid of an oxygen. We're getting rid of a carbonyl. So we want to remove this carbonyl over here. But here's the problem. If we use reagents that will take out carbonyls, how can we stop it from taking out this one? We only wanted to take out one. So we need to use a protecting strategy to do this. So think of this as, giving one of these carbonyls a shield to protect itself from our reagents. And that's going to be our first step. And in this case, the protecting group we can use there are a few we can use, but the easiest one for you is called a diol. This is called a diol. And we need to add it with H+. So we need a diol and H+. And actually, I'm not going to draw the arrow pushing for this, but what's going to happen is one of these will turn into not a carbonyl. It'll become a cyclic acetal. That's what it's called. And it'll convert this one, the aldehyde, into what's called a cyclic acetal. Now, the reason why the aldehyde will convert and not the ketone, they're both carbonyls, but not the ketone, is because the aldehyde is more reactive than the ketone, because there is less of an inductive effect. There's a more polar effect on this carbon. Sorry, not less of an inductive effect, but this charge on this carbon is not being shared by another carbon. It's being shared by a hydrogen, which is much smaller than a carbon. Over here, we have charge being distributed over 3 carbons. Over here, it's only 2. And so the carbon on an aldehyde will be much more reactive than a carbon on a ketone. So now we can react this carbonyl with something and not have to worry about it attacking the aldehyde, because we've protected it using a diol. We've made it into something else, and now it's protected. So now we want to think, well, what reagent can we use that will turn this ketone into essentially hydrogens, because this is essentially hydrogens, because that's what this is. And this is a very useful reaction. It's called the Wolff-Kishner reaction. Okay, and I'm not going to draw the arrow pushing for this. You can look it up if you're interested. But the way this is going to work is we're going to use 2 sets of reagents. So we need to add them in 2 steps. The first is hydrazine. We're gonna make the hydrazine. So the way you write it is NH2 or H2N, whatever, bonded to NH2, along with H+. So that's the first part of the reaction. And the second is going to be OH- and heat. Now this OH- can come from anywhere, from KOH, NaOH, whatever, just OH. Not an alcohol though, like the hydroxide ion. It has to be the actual ion with this negative charge. And what we're actually going to get is we're going to get that conversion of the ketone into 2 hydrogens. And so boom, we are almost done We just need to undo the diol, the addition of the diol to form a cyclic acetal. So we have to convert this back into our aldehyde. So how do we remove the shield? Pretty simple. We just add acid, H plus. Or if you want to be formal, like not formal, but fancy, H3O plus. So 3 steps. First is adding the protecting group. Second is actually the 2-step Wolff-Kishner reaction. And the third is the undoing of the protecting. Unprotecting, if you will. Okay, so I guess this is dragging on a bit, but I'm explaining how to do these. Hopefully well. I don't know if I'm doing a good job. All right, number 7 is asking us to provide the Witting reagent. Witting reagent that we would use to form this compound. Okay. Now, very, very similar to number 1 in this problem, we're just going to disconnect the double bond to form our 2 possible compounds. So it's very similar. The only difference is really going to be that instead of NH2, we're going to have PPH3. So phosphorus with 3 phenol. You get the picture. 3 phenols. Oh my gosh. Maybe I should draw this better. Phosphorus with 3 phenols. 6. Okay. So that's what that is. PPH3. I'm not gonna, draw the whole thing every single time we need it. Okay. So this is actually what it's going to look like. Okay. And this is our Witting reagent. It's also called an Ylide. Ylide? Am I writing that correct? It's a Witting reagent. I forgot how it's spelled. I'm sorry. Witting reagent. Okay, now if you're very, 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 very clever, you might ask, well, why isn't this the Witting reagent? Why isn't this PPH3 and this the carbonyl? Now the reason is, all right, let's entertain that thought for a moment, that we have 2 competing Witting reagents. So let's say we have this as Witting reagent number 1 versus this as Witting reagent number 2. Because the key step here is, can you identify the Witting reagent? If you can identify the Witting reagent, you can just pinpoint the other as the carbonyl. But you need to be able to tell which one is the Witting reagent. Actually, the way we can tell this is because the Witting reagent itself is formed from an alkyl halide that's attacked by PPH3. So let's draw this out. We have to draw a corresponding alkyl halide, and the way we're going to do that is we're just going to replace the PPH3 with any halide you want. I don't know, let's go with bromine. And the way it works is actually the PPH3 performs a nucleophilic attack, an SN2 reaction on the halide. So now the question is, which of these SN2 reactions is more favorable? The answer is this one. Because you have a primary alkyl halide, so there's less steric hindrance to attack here. Over here, we have a secondary alkyl halide, right? There's more steric hindrance. And so this Witting reagent is going to be favored. So if you really want to check you want to go back to the bromide that will form the Witting reagent. You might ask, well, okay, but SN2 reactions don't form double bonds, and you're correct. You're correct. SN2 reactions do not form double bonds, which is why actually you can write this differently. You can write this like this. So PPH3 single bonded to a carbon, but you're going to give a positive charge to the PPH3 and a negative charge to the carbon it's attached to. And what you're going to notice is that this negative charge can just move here to form the double bond. So that's how that works. So in this case, the Witting reagent is it's going to favor the primary alkyl halide. Okay, and that's the reason why. So this is our Witting reagent. This is our carbonyl. Number 8. Okay, how many problems are there? Hold on. Oh my gosh, there are 16 problems. So we're about halfway through. I'll try to speed this up, but I'm also trying to explain this hopefully somewhat well. Hopefully I'm explaining this pretty well. Okay, this one, straight up, I'm going to tell you right off the bat, this is a Diels Alder reaction. This is straight up pure Diels Alder in its rawest form. Okay. Now, very clearly, this is our diene. We have a conjugated system. This is our dienophile. Now, I don't remember which take of this video this is, but in one of the previous takes, I showed you the mechanism for Diels Alder, the general mechanism. It looks something like this. I don't think this is the take where I do that. Okay, boom, boom, boom. And we get a cyclic structure. It's not always going to form a cyclic structure, but it's going to connect the diene and the dienophile. It just so happens to be that in this case, we form a cyclic structure. In this example here. Okay. So, the question is, who's going to attack queen? Well, this cyano group up here, this cyano group here is going to be an electron withdrawing group. And so this carbon is going to be able to attack. This moves in, this double bond moves in, and this double bond comes back out to attack at the other end, at the other carbon. Okay, so we're going to connect them now. Now, this might be really, really tricky to visualize, so let's draw them one by one. Because this compound is really weird to look at, right? So maybe if we look at it like this, it'll be better. So we agree that we're going to be down to one carbon-carbon double bond for this compound. So it moves here. So let's try to orient our heads this way. And what's happening is this carbon, I'm going to label it carbon 1, is going to attach to this carbon here. I'm going to label that carbon number 2. And let's say that this carbon, carbon number 3, is attached to carbon 1. 4, 5. Maybe I should have started that with 2, but yeah, whatever. Okay, so this is going to be carbon number 3. I don't know why I wrote 1 there. This is going to be carbon number 3. And this is going to be carbon number 1. Now, carbon number 1 gets bonded to carbon number 2. So if we draw, let's say we draw this, right? Let's say we draw it. This is supposed to be an H, by the way. Nothing's going to happen to this over here. The Ca is the cyano group. And this is carbon number 2. Well, it forms a bond. And in a similar way, carbon number 5 is going to form a bond with this carbon here, carbon number 6. Now you might say, well, this is really, really ugly to look at, and this is really hard to visualize. And I agree. This reaction is this. I hate this reaction mechanism so much. This is a monstrous mechanism. But the way we want to visualize this is we're actually almost like joining two rings together. And so you might have heard your professor or your book use this term. It's called a bicyclic compound. And the way we want to draw this is we want to form what's called the bridge. Okay, so this over here, think of it as like a bridge connecting the two carbons that are going to be involved in this reaction. Carbons, in this case, 1 and 5. You could probably come up with a better numbering system than I can. I'm doing this. Of all the takes that I've done, this is the farthest I've gotten without, misspeaking and doing a problem incorrectly. So give me a break, right? So this carbon 1 that's being attacked by the dienophile, and carbon number 5, actually, if we're going to be accurate, that's attacking the dienophile rather. We're connecting them using the bridge. So if we really want to make this more messy, these three carbons rather are going to form the bridge. So bridge, bridge, bridge. It's conserved all throughout. And then down here, over here, this group of here, this is the 2,6 bond, or I'm calling it 2,6. We're going to put the double bond here. We can ignore the hydrogens for this. And finally, the cyano group, like this. It's going to be facing downward in the endo position. Diels Alder favors the endo position, in which any substituent groups are below the bridge. They are favored if they go below the bridge. Why is that? It comes from the orbitals that form. So remember that these are going to have p orbitals. So in this conjugated system, the p orbitals are going to be oriented this way. You probably don't need to know this, but just in case it comes up. And overlap between p orbitals forms stability. Now, if we have the endo position for our cyano group, well, this carbon can have its p orbital oriented like this, and that's going to form some very nice overlap in these p orbitals. That's very stable. On the contrary, I'm going to erase this for a minute. If we had it facing upward, that's not going to be as much overlap, is it? And I know that this isn't to scale technically, but understand that it's because of the bridge. Remember that this bridge is going up. So if your functional group is facing in the same direction as the bridge, it's further from the ground level where you have these p orbitals. Okay, so that's what the bridge is, and I hope that that was a somewhat decent explanation of Diels Alder. I know it kind of got messy. Sorry. All right, for number 9, we want to find two routes to go from an alkyl halide to a carboxylic acid. 2 different routes. And these arrow pushing mechanisms are not that fun. So I'm not going to go over the arrow pushing. We've already seen one of them. So let's take our first path. Like, let's say we ask Google Maps, hey Google, show me a path from alkyl halide to carboxylic acid. Well, the easiest one, and this is the one that I would prefer to use, I'd prefer to use this one, we're just going to make this into a Grignard reagent. And then we can just add this to a 2-carbon chain. So, not 2-carbon chain, because we already have 3 carbons. We're just going to add this to a C with 2 oxygens. And then we always have to add the, not always, but in this case we have to add the H+. And we're going to end up with this. So this is a very useful way to turn the alkyl halide into the carboxylic acid. We turn it into a green yard with magnesium and ether. Ether is the solvent. It's not going to participate in the reaction. And we're just going to add it to carbon dioxide and acid. This is a very useful way to do this. This is my personal favorite. I know I'm not... This isn't... at this point, this is not turning into a professional video. This is just turning into me talking. I prefer this method. The second method, it's also fine. They're both fine. In fact, this second method might be easier to do or memorize in some cases. But we're going to use NaCN, so cyanide, a cyano group with the alkyl halide, and it's just going to do an SN2 reaction. So we replace the CN, the bromine with CN. And finally, we're going to add acid and form the carboxylic acid. Now, this is also perfectly fine. This is perfectly good. You can do this. It was not the first thing that I thought of. Also because depending on where you are in your organic chemistry path, if you're doing these problems, you've already done the green yard. This should already be known to you. This mechanism here, however, you might not have learned it yet if you're at this point where you're doing Diels Alder and Fischer esterification. But you've definitely already done green yard. At least I hope you've done green yard. What are you doing at this video if you haven't done green yard yet, honestly? I'm kidding. Please like and subscribe. That's my promo. But yeah, these are both perfectly fine methods. They'll both get the job done just as easily. Comment how many times you think I've had to do takes of these reactions, and how long I've been, standing here. Why can't I erase that? Okay, that's going to be bugging me for the rest of the video, but we're just going to have to roll with it. 10. 10 is, okay, let's draw this out. Hopefully, you can tell what mechanism we're going to be going by here. And this is an oxygen. Okay? I'll give you 5 seconds to think of what mechanism this is. I don't know if that's 5 seconds, but I counted it. This is the Diels Alder reaction. See? I told you we'd be doing a lot of Diels Alder. Diels Alder. And so this one's pretty straightforward. It's definitely a lot more straightforward than the bicyclic monstrosity that we saw earlier. We're going to take the dienophile, attack this terminal carbon, bring a double bond in, and attack it back out. And we're going to form... It's always good to label the carbons so we can keep track of them. So 1, 2, 3, 4. 1 gets bonded to 5. Oh, wait. Did I really do that? This is 5 and this is 6. I can't believe I did that. Okay, 1, 2, 3, 4, 5, 6. We get a 1 to 5 and 4 to 6 double bond. Not double bond, but bond. Boom, boom. Okay. So this is pretty straightforward. Now, what if your test gives you a little bit of a monkey wrench and says, show the stereochemistry? Well, as we saw in the previous, what number was it? If you want to go back and see it, it was number 8. We showed that the Diels Alder will favor the Endo product. Oh, I forgot this double bond here. It'll favor the Endo product. Okay? Why? Again, because of the overlap. Wrong. The overlap that you want to form with your p orbital. So Endo is facing down. Even though we don't have a bridge here, endo is still going to be facing down. And so, if you remember, the way we show downward facing away from your page is using a dash. And if you want to get really fancy, you can put your H's on wedges out here, but it's not necessary. It's not necessary. Okay, that's Diels Alder. I'm going to take a drink really quick. Hold on. Number 11 is another organic chemistry 1 reaction, actually. It's also Orgo 1. But we're going to cover it here anyway, because it's, well, no spoilers. Okay, and we're going to react this with, firstly, mercuric sulfate, sulfuric acid, and water. And second, H+. Okay, now if you remember this from your alkyne reactions, be careful here, this is an alkyne, not an alkene. If you remember from your alkyne reactions, this is the Markovnikov addition of HO, or OH, you know it as OH, whatever, they're the same thing, you get the idea. And so we're going to add it to the more substituted side. We're going to add an OH group. In that case, that's this carbon. So I'm just going to bring that here. Okay. And it forms a chemical species called an enol. This is called an enol. Now, this is not stable. This is not a very stable form here. And I'm not going to go into the thermodynamics of it, but what you need to know is that this enol is not stable. It's not favored. And if we want to actually show this as a carbon skeleton, there you go. It looks like that. That's not stable at all. And it's going to do something called tautomerization. Tautomerization. And it's a reaction that's in equilibrium, and so it can go back and forth. But it's going to heavily be favored in the forward direction. And all this is really doing is moving where the double bond is. So instead of a carbon-carbon double bond, it forms a carbon-oxygen double bond. And that's why it's called keto-enol tautomerization. Because it's going from ketone to enol and enol to ketone. So here we form the ketone. Tautomerization. So just remember that this double bond it's moving up, back into a different position. My laptop is acting up a little bit. I don't know if it's because I've been at this for so long. Okay, number 12, we have 2 Diels Alder reactions. I'm getting sick of these Diels Alder reactions, but it's in our review. So for 12A, we have this diene, and we have this dienophile. Let's see. Is that right? Yes, that is. Now, this is what we call an asymmetric diene. So it's asymmetric. Did I spell that correctly? I did. Okay. And we call it a 2-substituted diene. The reason for that is if we start labeling the diene's carbons over here, so 1, 2, at 2 we get this methyl substituent. Now, a key thing that we want to remember, if your test does not require you to draw the arrow pushing mechanisms, then don't waste time. You can safely assume in this case that if you have a 2-substituted diene, you will get the 1,4 product. And what does that mean? Well, we still have to do the disconnect here. Not disconnect, the connecting here. So we know that we're going to get a 6-membered ring. We know that there will be a double bond here. This methyl is not going to change positions, but we're going to form the 1,4 product. So if we start labeling at this carbon, 1, 2, 3, 4, it means that this functional group will be positioned at this 4 carbon. And so that is our answer for 12A. Got it? So 2 substituted carbon, a diene, not carbon, 2 substituted diene will form a 1,4 substituted product. Is this... Oh, that's bugging me that's staying there. That's okay. For 12B, it's a very similar concept, except instead of a 1,2 substituted, instead of a 2 substituted diene, we just have a 1 substituted diene. So this is at the terminal end of it. This OCH3 group, or OME, is the same thing. And a CN. Now, again, we need to figure out the orientation of our product because these are asymmetric dienes. So, asymmetric diene and also an asymmetric dienephile. But let's focus on the diene, because if we can figure out the diene, we can figure out the dienephile. So, what's actually going to happen here is the lone pairs of the oxygen, we can imagine them forming a double bond. They're going to go back down. And it's not really going to perform a Diels Alder on itself. That's not really what it is, but it's going to kind of look like it. Because we can imagine this happening. So we have a partially positive OCH3 double bonded to a carbon. So it's going to kind of look like half of the Diels Alder has already been done. And in this case, over here, we want to figure out where the charges are going to be. Well, the CN group is a very good electron withdrawing group, and it's because actually what's happening here is a carbon-nitrogen triple bond, and this nitrogen has a very high partial negative charge. So what's going to happen is the whole carbon chain, this whole thing, has a very slight partial positive charge. That makes it very good, very ripe for attacking from a partial negative charge here. And in that case, that's going to come from this carbon double bonded to an oxygen with a partial positive charge. Okay? And so it can react like this. So if we have a partial positive here, it can attack. And that's where we're going to get, and then obviously this is going to come back out and do some attacking at, actually this will come out and attack at this end. And so our final product is going to be looking like this. So we connect, in this case, carbon 1 with carbon 2. We have to be careful that it's almost going to look like we've flipped around the dienephile. Okay, so we will form the 1,2 product. 1,2 product. All right. Oh my goodness. What's wrong with... Okay, we're gonna move to a different part of the board because that's bugging me. I don't like how that's just staying there. I might have to close out whiteboard and fix that. But if I close it out, the stream will probably stop. Not the stream, the recording will probably stop. Number 13. Here we are given a ketone, very standard ketone. This is the most simple a ketone can get. And we're given 2 moles of an alcohol, in this case, ethanol, and H+. Now, this is a very standard formation of an acetal. What's going to happen is we're going to imagine this O double bonded to the carbon being replaced with OR. And this, it's going to work in a very similar way to the Fischer esterification. So I'm not going to draw it out again. It's not exactly the same. But it's very similar in concept. So if you can draw the Fischer esterification, and you really need to draw the mechanism for this one, you saw how long the Fischer esterification was. I wouldn't. I personally wouldn't waste time going over the whole mechanism again on a test. But if you're just studying, feel free to try. But because this is already dragged on for a long time, I'm not going to drag on with that. So following this mechanism, this general formula, our R is CH3CH2, or a 2-carbon chain. So we're just going to add 2 carbons here. And that is our answer. I promise we're getting to the end. This took my professor about 50 minutes to get through. So I'm explaining it much slower than he did. Okay, next we want to start off with a product, actually. Okay, and we want to give the starting compound, whatever. And it can be starting with carbonyls. These are given in the problem that I'm reading from. It can start from a carbonyl, it can start from an amine, or it can start from an alcohol, or some combination of those 3. Now, I'm just going to tell you right off the bat, there's no amine involved here. There's no nitrogen involved. So we're starting off with carbonyls and alcohols, rather. We're going to need both. And remember the acetal general formula that we saw earlier. So I'm going to draw that out again. Remember we went from a ketone to an acetal using ROH. So if we stare at this long enough, and I'm going to point this out now because hopefully when you're taking your test or when you're in the lab, you'll be able to see this. What we're actually doing is that we're identifying the carbon that's attached to both oxygens, and anything below that is more or less not going to be in this reaction. It won't be the final product, it won't be changed in the final product of this reaction that much. And it's going to be attached to 2 oxygens with the R's. So let's try that with our compound for number 14. Is this also something I can't erase? Okay, I was able to erase it. Well, this is the carbon that's attached to 2 oxygens. Okay. Now what's our R? So let's try to follow the chain here. Well, actually, all of this is our R. Now that's very interesting, because it means that since we're forming a cyclic structure, that there is no distinction between this single reagent that's the ketone and this single reagent that's the alcohol. It means they're on the same compound, because it's almost like and you'll see what I mean when we draw the starting compound. Okay, it's almost like it's folding in on itself. So the way you want to approach the strategy is let's disconnect it here. Okay, I'm going to label this carbon 1. Okay, carbon 1 is going to be double bonded to an oxygen. That's our ketone. Okay, now this is the kicker. We're going to call this carbon 2. 3, 4, 5. So 3, 4, 5. And at the end of that, we have the OH. And now you should kind of be seeing where we're going with this, or where this went. It's almost like, and this isn't the exact arrow pushing, but it's almost like these OHs folded in and attacked this carbon at the other end of the double bond. And replaced this with, actually, if you've taken biology, this is going to release H2O. That's why sometimes in the mechanisms you'll see minus H2O. And that's how you'll get this. So this is a dehydration reaction as well. It's going to release H2O. So it's a little bit tricky. This one's a much trickier version of some of the problems that you might see on your homework. It is a little bit tricky, especially when you have these rings. Number 15. I promise. I really promise that this is the last. This is the last Diels Alder. I forgot how long I've been talking, but this is the last Diels Alder. I promise. Okay. I just needed to get a drink. Okay. So in this case, this is our diene. This is our dienophile. Now let's not mind what the CO2CH3 is, because it's on both sides, right? And so, actually, the way I wrote this is a little bit confusing, so let me rewrite it. So you know that this is CO2CH3, and these are distinct compounds. Okay, it's just a really long formula. Okay, now the trick is that actually, so if you really think about it, no matter which way you flip it, you're going to get the same general structure. You're going to get, here's the arrow pushing, by the way, it's standard arrow pushing. You're still going to get your 6 carbon chain, ring rather, not a chain, with the 2 methyls, and then your CO2, CH3, CO2, CH3. Now look at this dienophile. It's a trans. It's in the trans conformer, which means that if you really think about attaching these two together, if one is in the endo position, so let's say that this top one is in the endo position, the other one has to be facing the other way. So it's going to be facing up. And these will be, if you have 2 carbon chiral centers, remember that these are called diastereomers. And if you really think about it, there's really no way of predicting if you're going to get this as your wedge or this as your wedge. And so what we have to do is draw this. We don't have to do this, but we have to indicate that there is another possibility in which the stereochemistry is flipped, in which this one is on the wedge and this one is on the dash. And instead of drawing it out again, we can just write that we're going to get the enantiomer of that, or en. We can just indicate that. Okay, this is the last one. Oh, you know what? It turns out that this last one is a 2-parter. Sorry. This one's pretty standard. We're going to go through it. Okay, this one, again, we're starting off with an alkyl halide, and we want to convert it into an aldehyde. So, halide, alkyl halide to aldehyde. Okay, the way we want to do this is, okay, actually, there are different ways we can do this, but the most easy way to do this, and the one that I recommend that you use, notice how we're preserving the carbon chain. We're just changing functional groups. Okay? And when we are changing functional groups and their positions on the carbon chain, we want to think of creating, that's my phone, I'm sorry. We want to think of creating an alkene. Okay? And then we can add functional groups to different ends of the alkene. So how do we create an alkene from this alkyl halide? Well, we need elimination. And in this case, we want to avoid this alkene. This is not favored because we're adding to the ends of these carbons. Oh, that's not a carbon. Not here. So we want the less substituted alkene. We want the less substituted alkene. How do we get the less substituted alkene? We need to use a bulky base. So TBUOK is the go-to bulky base. Not going to draw the E2 mechanism, but there you go. And now we can focus on adding another functional group to the other end of this carbon. So again, we want to create a less substituted functional group here. And we want to approach this by, well, actually, let me see if, because it's not necessarily intuitive to do it this way. Maybe you can figure out the whole alkene thing, but at this point, a more intuitive way to think about it might be, how would we get here? What kind of reaction, intermediate before this would be most favorable? And, well, an alcohol would be nice. The reason for that being, we can just oxidize this alcohol into its aldehyde, and we can use PCC or DMP. What we cannot use is, do not use Na2Cr2O7. The reason being, if we use that, we're actually going to get the carboxylic acid. This is too strong of an oxidizing agent. It's way too strong. So we want to use a weaker oxidizing agent. These are weaker. Okay? So that's why we use PCC or DMP. Okay, so now we have our first step, we have our last step. How can we get from this alkene to this alcohol? Well, we're going to add OH, but in the less substituted position. So the less substituted position. Okay, now how do we make sure that the OH adds in the less substituted position? Well, we're actually going to use hydroboration oxidation. So for hydroboration oxidation, you have to remember the reagents are BH3 THF. THF is not a reagent, by the way. It's a solvent. And H2O2 OH. Okay, so hydroboration oxidation will add the alcohol to the less substituted part of the alkene. Less substituted carbon. I don't know why I'm screwing up that name. Okay, so that's our pathway to do this. I'm sure there are other ways you could do this, but that's probably the easiest and most efficient. Last one. This is the last one. I don't know how long this has been going for. It's probably over an hour at this point. But these are a lot of problems, and these topics are a little tricky to explain. Okay, we're starting off with this compound, and we're going to make this ketone. Again, the carbon chain is staying the same, carbon skeleton is staying the same. Okay, now what to do here? If we start moving forward, at least for me, that's not very intuitive, right? Like, it's very hard to figure out what you're going to do next. So let's try to work backwards. Well, if we see a ketone, we know that the easiest thing to do is to start off with an alcohol, because alcohols can be converted to ketones pretty readily, and we have the reagents, PCC or DMP, almost the same as last time. The key difference is that here we can actually use Na2Cr2O7, sodium dichromate. Now, we couldn't use it last time because we were on a primary alcohol, okay, and it would have converted this into a carboxylic acid. But here, since we're on a secondary alcohol, this should be fine. It will stop at the ketone, and I think there was a previous problem where we had the same concept at play. Okay, well, now we're thinking, okay, how could we have gotten this alcohol onto this ethyl group? Well, remember that you can add functional groups to a carbon skeleton if you add it to an alkene. So alkene reactions. So maybe this came from an alkene. And we can't have the alkene here because that would violate the octet rule, and it would screw around with the resonance of this. So, okay, this looks pretty reasonable. What reagents could we have used to get to this step? Well, there are actually two main pathways we could have used, two kinds of alkene reactions. I'm going to give myself more space to do it here. The first path would have been to just use acid and water. That would have been the first way. And this would have been the easiest way because this is Markovnikov addition of alcohol. The second way to do it, which would have also gotten us Markovnikov addition, would have been the process of oxymercuration, demercuration. And I'm not going to draw the arrow pushing for that. But in essence, the main reagents we're using are HgOAC2, H2O, and this has to come in the second step. We have to add NaBH4, and it's OH, NaOH. Okay. Okay, well, how did we get from this alkyl chain to this alkene? Well, we could have done elimination to get there, but there are no good leaving groups over here on this benzene, on this initial product, initial starting compound to get benzene. So maybe we added a good leaving group. Well, a good leaving group is bromine. Bromine's a pretty good leaving group. And we performed an E2 reaction, and this E2 reaction gave us the less substituted alkene. So just like last time, we used TBUOK as our base. And then finally, how did we get from our starting compound to the brominated version? Well, we brominated it. So we used Br2 and light. And it put the bromine in the benzylic position, which is the most stable place for a bromine to be, because if we were to replace it with a carbocation, this could be stabilized by resonance. Okay, so I don't know how long that lasted. That was probably close to an hour and a half, if not longer. Probably way longer than an hour and a half. That's how long I've been talking. I'm gonna go eat. I hope this helped you with your chemistry problems. And yeah, bye.